So, and I'm not sure if Chris, how can he ask questions, but let's speak with the real people. Colton in my left, boy, I'm not surprised.
What's that supposed to mean? Really enjoyed that. Exciting stuff. You mentioned that 56 qubits was important. Was that like computationally interesting or just technically difficult? And is there any threshold you have in mind where you think this becomes a very big game changer almost overnight?
Yeah, so around 50 qubits is where it becomes really hard to do this full state vector simulation, right? So that's why I said 56 is important. Not, 56, 54, that didn't really matter, but being above kind of 50-ish qubits kind of gets you into this game where now you can do this very, albeit very contrived problem, but do this problem that is going to be very hard to do classically, right? And this is, the first time people had done it in trapped ions, as one of the only a handful of demonstrations, and in many ways was like, higher circuit fidelities for similarly difficult problems and things like that. So, it's one of those, there's going to be a lot of quantum computing milestones. I think doing this stuff is a quantum computing milestone, doing error correction beyond kind of break even. There's a lot of ways to define break even within that. Starting to do algorithms on the logical level. These are all big milestones that are, happening now or will be happening soon in quantum computing.
So I will ask a question.
Okay.
One of the funny things of doing multi-core work is that I get to be in front of things that I have absolutely no clue. So I try to learn. So I invite people, some answers. I wrote to Peter Shore, but he never answered. And I wrote about 3 times. But the same time I see the news today, Jeff sent me about Microsoft, and influencers say that, well, the world just have changed. While you and Chris says, well, this is just a little bit of crap. But on the other hand, you are partners with Microsoft.
For the record, Chris said it was crap. I don't think I said it.
So what I'm trying to ascertain is how can we, the other 99%, deal with all this?
Yeah, it's a great question. I mean, this is kind of why I brought up the benchmarking stuff, right? It was kind of a quick aside, but we need to kind of, as an industry, drive to a little more openness with data and being, I think Microsoft did publish 2 papers on the archive last night. I feel like maybe some of that was being driven by how we've dealt with these things, and others in the industry have dealt with these things of like wanting to see data. I haven't had a chance to read them, having been quite jet lagged last night, but I think some of my colleagues have read through it. It sounds like it's not, in the papers, they're maybe not so definitive of whether they saw the true topological phase they're looking for. But your point stands, like, it's a very complicated subject, right? Even experts struggle with how to benchmark these things. There's a lot of claims. It's tough to like sort through them. I don't have great answers. I think we have to.
Perhaps my point is that you guys could do a better job of selling what actually is happening. Because, I mean, let me give you 2 things. I can say, yeah, Multicore World is a fantastic conference of less than 1,000 people. I'm not lying. But you start to circulate that, and someone say, oh, there are hundreds and hundreds. And that's how you create a bubble. Let me give you a completely different approach. I've been on tech for a long time, but I live in a very small town 3 hours from here, surrounded by farmers. My lawyer, he retired, but he deals with farmers 95% of the time. So when I come and say, hey, I have this situation, I have my company, what do? I do this, parallel computing, Intel, but it's a little bit here and there. And he just listened. And at some stage say, and that has something to do with quantum computing. And what can I say? So, I mean, people try to grab whatever hears from here and from there and put it in front because they are literally afraid to say, I have no clue what are you talking about. It's human nature, but it's counterproductive because it creates an aura of mystery which only detach from everything else. I mean, you are supposed to be building something cool. And someone is selling something like, I understand you need to keep the shareholders, the investors, that's normal business, right? But I feel that there is, I used an example earlier today, NFTs. That was fast, that lasted, I don't know, 1 year. Quantum is here to stay, but are you present, what's the selling point? I mean, Honeywell, what's the selling point? Quantum Cambridge or Cambridge Quantum was suddenly you merge. So it's much more, there's much many people who have no clue what you guys doing than the ones who do.
How,
What was the question?
Merry Christmas.
Yeah. Yeah, I mean, I hear what you're saying. I think, I can't answer to all of the things that have been said in the community, right? Like, we're responsible for what we say, and even there, like, it's very confusing because you need all this background information to even wrap your head around, like, what is this milestone? But I do think there's real progress here. I think some of the stuff I showed was real progress, right? It's not just hype. Like, you want to try and be honest and say, yeah, this is a very contrived problem, but it's a big deal that, like, a quantum computer did something that you couldn't do classically, right? That's a big deal. When we solve some physics problem that you couldn't solve, like, yeah, that's not the multi-billion-dollar economy-changing thing, maybe, but it is a big milestone to do that. It is a big milestone to see quantum error correction actually start to work. And this thing that, at first glance just shouldn't work is actually, like, I think the fact that it's possible is kind of amazing, quantum error correction. So I think we have to, we have to be careful of what we claim, and there are some claims that are just ridiculous, but we also can't completely undersell that progress is being made. And I think, one important point I didn't make that I probably should have is, this 2 to the 100, that's this crazy big number. If you have 10 qubits that are all high enough quality that you can entangle them, well, that's 2 to the 10, that's 1,000, that's a toy problem, right? So it goes very quickly from, like, this thing's a toy to, holy smokes, right? Like, this is impossible to simulate classically, and that's that's why there is going to be this big ramp. If you have these near-term applications that are really exponentially advantageous compared to classical computers, it can go very quickly from, like, who cares to, oh crap, right? And it's tough to explain that, right? It's tough to wrap your head around exponential growth in a lot of ways, right? Which is
COVID?
Yeah, right. It's a fundamental human failing of, like, trying to understand exponential growth. But yeah, it's a hard problem.
Jeffrey.
Hey, you mentioned the entanglement during your presentation. I was just wondering, in the big picture, has there been any progress in understanding entanglement since kind of the quantum computing revolution has started? Have there been any even mild breakthroughs in making progress on that?
Yeah, quantum mechanics is funny. It's described by some of my professors as simple but subtle, right? Like, it's also, I think every graduate student who's taken a quantum mechanics course has been told at some point, shut up and calculate, right? So there's this, it starts to push your boundaries of what does it mean to understand something, right? This comes back to this, like, scientific method. What does it mean to know something? What does it mean to understand something? Like, because our experience is so classical, right? That when we say we understand something, it means a lot of times it just means we have intuition, right? And it's tough to build that intuition when you're not experiencing it. And I think there's like good tools now to try and have, with computers to set up little experiments where people can experience quantum, right? And then they feel like they do understand it more. But I kind of feel like we understand it, we're just not comfortable. And maybe we'll never be comfortable, right? And maybe the next generation, if they're exposed to it more and earlier, this like why do we die question that came up earlier, maybe that helps, right? The next generation, maybe my kids will be more comfortable with it. So I'm not sure that there needs to be a breakthrough. I think we get the math, we can calculate what's going to happen in these experiments. We're just not comfortable with it. That's okay, I think. Yeah.
Jim.
Hi, Russell. I was curious. I don't think you talked about temperature, but what temperature or environment do your ion traps need to be maintained at?
Yeah, so we use liquid helium to cool not our qubits. We cool the qubits with lasers, right?
Okay.
And we cool the vacuum chamber is really the biggest thing. The trap itself we want to cool because there's this thing called anomalous heating where you have fluctuating patch charges on the surface and it creates some heating of the ions, the qubits. But the biggest thing that's not really limiting us. The biggest thing that limits us that we need cooling for is just the vacuum pressure. We have very, very low vacuum pressures in these chambers, but by cooling to 4 Kelvin, like things stick to the walls, so you get a couple orders of magnitude better, right? So that's what. But Chris and his team sometimes operate at room temperature. We've done it before. We don't make our commercial computers at room temperature because this 2 orders of magnitude is nothing to sneeze at as far as vacuum pressure. It just makes your life easier and it's just worth it. But we don't need these dilution refrigerators. The laser cooling can actually get you down to kind of like micro Kelvin temperatures, and below if you really push it. So you basically get down to this motional ground state of this harmonic oscillator that you have in your ion trap. Yeah.
Okay. Well, part of the reason I ask is for like quantum chemistry problems, it may be possible to decompose a portion of the application to run in a quantum computer, while there's another portion that runs in a classical computer. Have you been thinking about those kinds of applications?
Yeah, for sure. And I think we recently moved a machine to Tokyo. You may have seen this.
Oh yeah. Yeah.
And they just recently had a press release where they talked about they integrated this supercomputer in Tokyo with our quantum computers so that you can explore some of these classic quantum sort of coded, co-algorithms.
It's actually in Kobe, right, at the Riken Institute.
The Fugaku is the supercomputer, and the Waku is where the quantum computer's at.
Oh, okay.
And so then you can question like how low latency do you really need between the supercomputer and the quantum computer. It depends on the application, of course, but to the point, like the quantum resources are so expensive compared to the classical, right? Like you should do everything you possibly can on the classical computer and save the quantum computer for the really hard bits where you have say like entanglement in your system and you need to simulate this highly entangled quantum system, but lots of it can be described classically. So you describe what you can classically and then save the quantum resources for where it has the most impact.
Right. Okay. Thank you.
Join me saying thank you to Russell for the fantastic talk.